for allowing me to talk a little bit about mathematics, even it's a phenomenology conference. So as the title says, I want to talk about non-geometric fluxes and its relation to Poisson geometry. At first, I want to just very briefly motivate the algebraic structure which we are considering, and then I want to present you two representations of the algebra, and I want to say something about it. So let me begin with a very, very brief and incomplete introduction to the algebraic structure. So it's a very well-known story. If you start with this action and do a reduction on it, for example, on a d-torus, you get the ODD invariant action, which you can gauge. So this you can gauge a subgroup or the whole ODD group. And then you get gauge generators which corresponds to the vector fields which come from the Kaluza-Klein reduction of the metric and the B field. And what you can show is, or you can make at least the most general ansatz for the commutation relations of the gauge generators, which is given by this one. And it is conjectured that all these parameters should have to do something with this chain of fluxes. So if we start with the H flux and do one T duality, we get a geometric flux. Doing another one, we get a Q flux, and doing still another one, which is more or less a conjecture, we get something which is called the R flux. And what I'm going to present you is a realization of this algebra in two different ways. The first one was already mentioned by Rolf. It's a representation on the tangent bundle of a manifold. So forget about what kind of manifold. Let's just take the tangent bundle. Let's take a basis and a dual basis, and where the geometric flux is given by the commutation relations of the basis. And let's also assume that there exists a bivector field, which defines as a map from the cotangent bundle to the tangent bundle, just like this, which allows us to define also objects with index up. It's just an easy sum. And because we are in the tangent bundle, we can easily compute commutators of vector fields. And if you take these definitions, I mean, if there are some experts on non-geometry, they will maybe recognize these combinations. If you take those, we can show that if you just calculate the commutators on the tangent bundle, we get this algebra again. The advantage of the realization on the tangent bundle is that you can very easily calculate relations among the fluxes. So we know that on a tangent bundle, the Lie bracket fulfills the Jacobi identities. So calculating all different Jacobi identities, so for these objects with index up or also with the original tangent vectors, we get relations among the fluxes which should be true. So that's a way how to get Bianchi identities for the non-geometric fluxes. And they turn out to be very important in that what I'm saying afterwards in the second realization. So I don't want to say any more about this realization because already Rolf talked about it. What I'm focusing on is the representation on the direct sum of the tangent bundle and the cotangent bundle of a manifold. For this, I want to introduce, so that's the only definition which I mentioned, I'm sorry about it. But this is really an important object. So that's a good thing. Okay, so thanks a lot. So I want to mention at least this definition because this is basically the most important structure in the paper which I'm talking about. So let me define it. So if you take a vector bundle and you have a bracket on it, and in addition there's a bundle homomorphism which is called anchor, which maps your vector bundle to the tangent bundle. Then if you have in addition the Leibniz rule like this, so you can pull out the f, and you have an additional term where you map the section on E to the tangent bundle, let it act on f, which gives you again a function which you can multiply with s. Then this is called a Lie algebroid. So this is the basic mathematical structure which we are dealing with. What one can easily show is that if you take the dual space of E, so if this is satisfied, one can easily show that this type of thing is the definition of a differential on the cotangent, on the dual space of the vector bundle. And we use this later on to get relations for non-geometric fluxes. So this is, I think most of you know such a definition. Like, for example, the de Rham differential is abstractly defined like this. So let me give some examples of the structure. So the most easiest one is the tangent bundle itself with a Lie bracket. And as an anchor, we take just the identity. And the differential, which I mentioned before, is then really just the definition of the usual de Rham differential. So for example, the H flux in physics is just the de Rham differential of the B field. A more non-trivial example is the cotangent bundle. You have to take as an anchor the anchor which I defined before with a bivector field. So you need to have at least a quasi Poisson manifold, which is basically equivalent with the existence of such a bivector. And you have to give a bracket on T star M. So you have to have a bracket for forms. And this is what mathematicians know as the Kosul-Schouten bracket, which is defined like this. So you can take the Lie derivative of these guys, but you have to map one of the guys to the tangent bundle with the anchor. And in addition, you have the differential of this thing. So this is a nice bracket, and this you can show that this defines also a Lie algebroid, and you can also calculate the corresponding differential. But this is in this time the dual space of T star M, which is Tm, and you can show that this is given by the Schouten bracket. The Schouten bracket is just an extension of the Lie bracket to wedge products of vector fields. It's just a simple extension. And then you can show that this gives you a nice differential, but it's a differential for vectors. So that's nice. And it's defined by taking the Schouten bracket of the bivector with the object. So now let me tell you something about the physics. So for example, the R flux, which should be a trivector, can be written nicely as the derivative, so to say, of beta with this derivative. The next step is to include the H flux. So the story above, there is no 3 form, no H flux. If you want to include it, we have to make the structure a little bit more complicated. We have to do a twist, which leads to quasi Lie algebroids. For example, in the first case, this is just an addition of a term to the original Lie bracket, which modifies the bracket a little bit, but the essential structure, the essential property of the Lie brackets stay the same. And as one can see from the formula of the de Rham differential, also the differential will be changed because the brackets show up in the differential. And now if you evaluate this on the basis, for example, on 2 vectors, you get again the f which we defined before. So I could remind you. So this is this curly f which I wrote down before. You get exactly this. And you can also do this with the second example. There's a little, I mean, it's in principle it's the same. You add an additional term to the original Kosul-Schouten bracket, and you get also so to say a twisted differential on the tangent space. And if you evaluate this again on the basis, you get the expression for the Q flux which we had before. You can calculate directly. Okay. So what we want to do is to have a structure on the direct sum of Tm plus T star M. And for this, so this is the only thing which I want to cite because we work with this a lot. There's a result in mathematics which tells you if you have 2 such quasi-Lie algebras like Tm and T star M, there is an associated Courant algebroid structure on the direct sum. There should be some compatibility conditions, but I don't want to mention it because I'm running out of time. So what we proposed is take the following Courant algebroid structure on Tm plus T star M. We have first to define a bilinear bracket on this kind of object for sections, which we define in 2 different ways, one symmetric and one antisymmetric. And I have to give you a bracket to have a Courant algebroid structure. Yes, thanks. Thanks a lot. And we do it like this. So I mean, these are technical details. So here you can see this is the H-twisted Lie bracket, which I defined before. And you have, again, to add something. For example, if you have a bracket between a vector and a form, you have something like the Lie derivative of the form and the Lie derivative of the vector, plus an additional term which depends on this bilinear form. And you can do this for the bracket of a form in a vector and a form in a form. And you have also give an anchor, and as an anchor we take just the sum of the two anchors which we had before, the identity and the anchor with a beta field. And if we do this, I mean, this looks a little bit weird or a little bit complicated. I mean, one has to first prove that it's really a Courant algebroid. It has some axioms. And this was the first result. This is indeed a Courant algebroid. One can prove this. And a major step in proving this is taking the Bianchi identities which we had before. So you have to calculate some properties of the Courant algebroid, which only are satisfied if we can use the Bianchi identities. So this is where the connection from the Bianchi identities to the Courant algebroid structure is. And if we have proven this, there's another result. We can again directly realize the algebra. But this time we are not on Tm, but it's really the sum of Tm plus T star m. So we really have a bracket between vectors, vectors and forms. And you can now directly calculate that again, these fluxes which we defined before come out directly. This is an easy calculation. So let me summarize. So we started with some geometric data. The only thing which we needed is an H flux, a beta field, and some manifold. And we were able to give the realization of the algebra, which we had before, directly on the tangent bundle, which gave us some Bianchi identities by just calculating the Jacobi identities. And the other direction was introduce a new structure, the structure of quasi algebroids, which gives you a bracket, so to say, for vectors and forms. And you can show that we have the structure of a Courant algebroid, where you can again realize the algebra which we had before. So these are the two different realizations of the algebra. For this realization, you really need the Bianchi identities which we derived before. And what I didn't mention, so if you apply the anchor to the algebra on the direct sum, you get again the algebra of Tm. So this is another nice connection between the algebras on the two types of objects. Yeah, so that's the main way of thought, and let me thank you.
Questions?
Yes.
In your second slide, when you give the form of the algebra, you call it equation 2 or something in the beginning. Yeah, just a comment. The definition of the fluxes you have below really resembles, or at least to me, to the Ramon-Ramon-Gauge invariant formulation. That is just a chance. Is there any relation, or is this way of defining things in a recursive way?
So I have not thought about this. I mean, if it looks like the same, there should be some connection. But actually, yeah. So this is just a realization on the tangent bundle of some manifold. So I can't say so much about the connection to this stuff. But maybe if you tell me some more about this, we can discuss again.
Questions? These Bianchi identities,
yes.
Can they receive contributions from local sources like brains? And if so, can they be included in these formalisms?
Oh, that's a good question. So I mean, in this framework, we didn't talk about brains. So this is just a manifold, and we're just computing commutators of vector fields. Yeah. Let me think.
So it's not obvious.
It's for me, it's not obvious. So I mean, you have if you include brains, you have sources for fluxes. I mean, you should first define what is a brain on this manifold M. And then maybe there are additional contributions to these definitions. But I think if you have some sources, I mean, I'm pretty sure that you can include it also again in this algebra.
Okay.
But we haven't done this, but maybe one has to do this.
Okay. Okay, so let's take the speaker again.